How do you draw a titration curve for an acidic amino acid? Hello everybody, it's Skrillex with another BMSC 200 video. Skrillex, because we're talking about titration, and I'm about to drop the bass. Today, we are talking about titration curves. Now there's a couple basic. Today is going to be a long video. There's a couple basic concepts we're going to cover today. So I'm going to let you choose which topics you want to brawl.
General Titration.
So you want to learn everything about titration. Well, perfect, me too. As you've already learned, this is your amino acid backbone. On your left, we have our amine group, and on the right, we have our carboxyl group. Now, the tricky part about this is that depending on the pH of the solution that it's in, and the amino acid, the charge of this backbone can actually change. On our pH scale, lower numbers mean more acidic, and higher numbers are more basic. If you're taking BMSC 200, I hope you already know that. When we get more acidic, we're more likely to see hydrogen and positive charges. The higher we get on the pH scale, the more basic we get, the more likely we are to see negative charges and a lost hydrogen, and probably Uggs with a Starbucks. The reason I say the more likely we are is because there isn't a magic pH number where everything magically gains a hydrogen and a positive charge or loses a hydrogen and becomes negatively charged. If you look at our amino acid backbone, the amine group has a pKa of 10, the carboxyl group has a pKa of 2. What the pKa tells us is this is where the TSN turning point is for a group turning from positive to negative or vice versa. Our amine group will be positive or neutral, our carboxyl group will be negative or neutral. It all depends on the pH of the system. So if we look at our carboxyl group first, anything below pH 2 is going to have our COOH. Anything above will be negatively charged and just be COO. With our amine group at a pH of 10, we have the switch between NH3+ and NH2. This is the only time in your life where you don't want to be called a 10, because it means you're basic. When you put these two ideas together on a titration curve, we get a line that looks like this. And we have two places where the charge of our groups changes. At pH 2, the cuckoo kachoo changes, and at pH 10, our NH3 changes. So at this point, you should be able to figure out what the charge of our amino acid will be at certain pHs. If I said, what is our charge of this amino acid at pH 1.7? Is it A, -1, B, -2, C, 0, D, +1, or E, all of the above? Well, if this is Dr. Napper's exam, the answer is always E, all of the above, but the correct answer here is actually D, +1. Now, how did I figure that out? Well, let's look at our 2 points of changing charge. We're below pH 10, so we know that we have NH3+. And we're below pH 2, so our carboxyl group has to be neutral. 1 + 0 is 1.
Quick math.
If you look at our chart and do the fairly simple math, you can find that we have 3 zones. We have a +1 zone, a 0 zone, and a -1 charge zone. Now hopefully you're wondering, hey Mr. Skrillex, what about when the pH is exactly 2 or exactly 10? What happens there? To you I say, great job internet stranger, and I give you a patronizing pat on the head. At exactly pH 2 or 10, we enter a state of limbo, and not the kind you play on Friday nights. At these exact pHs, we don't really know whether a species will be positive, negative, or neutral. Instead, we just assign it a half charge. So filling in our diagram at pH 2, we have +1/2 charge, and at pH 10, we have -1/2 charge. Seems simple enough? Great, let's move on to diprotic titration.
Diprotic Titration.
As you probably already know, di is a Latin-derived prefix meaning two or double. So if you were to go to Tim Hortons and ask for a double-double in Latin, you would say, "Can I have a di-di?" With diprotic titration, we have two zones on an amino acid that change in their charge, depending on the pH. Which amino acids do you think only have two areas of charge? If you said all of the non-polar, aromatic, and polar uncharged amino acids, you would be correct. Everything except our positively charged and negatively charged amino acids are considered diprotic. Just like we showed last time, diprotic amino acids have two pH zones and two specific pHs where they change their charge, around 2 and around pH 10. At physiological pH 7.4, their charge is 0. Easy peasy, lemon squeezy.
General Triprotic Titration.
Now, triprotic titration is where it tends to get a little more confusing. We have 4 general types of titration. We have diprotic titration, which we already talked about. We have triprotic acidic, which includes aspartate and glutamate. These guys have pKa's of 2, 4, and 10. At physiological pH, they have a charge of -1. We have triprotic basic, which includes lysine and arginine. These have pKa's of 2, 10, and 11, and have a charge of +1 at physiological pH. And triprotic histidine, which has pKa's of 2, 6, and 10, and a charge at physiological pH of +1 over 0. Now, let's get into the specifics.
Acidic titration.
This includes aspartate and glutamate. Drawing out our graph, we know that we have 3 pKa's to consider. We have 2, 4, and 10. So drawing out our line, here's what our graph will look like. At the first junction, we have a charge in our amino acid backbone, transitioning from COOH to COO-. At this second junction, at pH 4, we have a change in our amino acid side chain from COOH to COO. Remember, this is on our amino acid side chain. And at the top junction, at pH 10, we have a change in our backbone from NH3+ to NH2. Now, this is the part where most people get stumped. Where is our point of 0 charge? Your point of 0 charge is right here. Now, you should be able to use common sense to figure the rest of these in. Remember, we said that at the exact pKa's, there will be a half charge. So at pH 2, we will have a +1/2 charge, making anything below it +1 overall charge. Moving above that, we have -1/2, -1, -1 and -2. So the acidic amino acids have the potential to go from +1 to -2, depending on the solution's pH. The basic amino acids, which we'll talk about shortly, have the potential to go from +2 to -1. The last thing that we need to talk about before moving on is the isoelectric point, or PI. This can be calculated with the following formula. pKa1 plus pKa2 divided by 2 equals our PI. Now for triprotic amino acids, we use the 2 pKa's that surround the point of 0 charge. For this amino acid we used here, we would take 2 plus 4 divided by 2 for our PI of 3, which is this point right here, and that's our point where our amino acid has 0 charge.
Basic titration.
Similar to acidic, triprotic basic titration has 3 areas of change in charge. Basic titration includes lysine and arginine, so here are those 2 amino acids and where their charges change. Our third pKa in this case is 11. You'll notice that the pKa of 2 and 10 stay the same, and that's because it has to do with your carboxyl group and your amine group respectively. So let's draw out our graph here. Here's what happens at the different places. At the lowest pH, we have the change in our backbone oxygen from COOH to COO. At pH 10, we have the change in our backbone amine group from positive to neutral, so to NH2. Now for simplicity's sake, I've said that we have a pKa of 10 for our amine group of our amino acid backbone. But when we're looking at bases, the pKa actually gets bumped down to around 9.16. If you look at slide 18 of your lecture notes, you'll notice this difference. And at pH 11, we have the change in our backbone from NH3 plus to NH2. So our point of zero charge is actually going to be right here. And then labeling the rest of the charges on our graph. Now, how do we calculate our isoelectric point? Well, remember, we have to take the two pKa's surrounding our point of zero charge and average those out by dividing by 2. So in this case, we have 9 plus 11 divided by 2, and that gives us our PI of 10, or our point of zero charge of 10. And there you have triprotic basic titration.
Histidine Titration.
Histidine technically falls under the category of triprotic acidic titration, but because of its weird ring structure here, the charges and changing pHs actually work a little bit differently. The pKa's for histidine are slightly different. The pKa's are 1.82, 6.0, and 9.17. The side chain that is going to be changing in charge is this nitrogen right here. Other than that, histidine titration works identically to acidic titration. We've got our distribution of charges here with our point of zero charge right here. And calculating our PI, we have 6.0 plus 9.6 divided by 2 equals 7.6. Hopefully this video has helped you better understand titration curve and will allow you to defeat that midterm. Basic.
Slow down, grab the wall, wiggle like